Hello, and welcome to this video on stud welding. To begin with, let me start by sharing the screen so you can follow along with the PowerPoint that I'm going to use. My name is Girish Kelkar, and I am a welding consultant operating as WJM Technologies. Additional information about my consulting business is on the web at welding-consultant.com. Today, we're going to focus on stud welding. Stud welding is a very unique process commonly used in some industries to attach a bolt or a stud. It can be either a straight bolt or a threaded bolt to one side of a plate or a metal piece, usually sheet metal or a plate. And it is very commonly used in industries such as construction, shipbuilding, vehicles, electrical enclosures, and household appliances. The main positive attribute about this process is you do not have to drill holes into the base metal to make that connection. So that is one of the fundamental benefits of this process, and apart from being fairly easy to use as well. There are many videos on YouTube which actually show the physical process of actually taking the stud, loading into the gun, and making the weld, and the whole thing happens in a flash. So it's very hard to actually see the process in that sense. So in this video, we are actually going to focus on reviewing the fundamentals, not actually viewing the actual process. Here's an example of 3 stud welds. This one on the left shows a stud where a part of the stud is threaded. In some cases, the entire stud can be threaded. The weld in the middle shows a stud with a tapped hole in the middle. And the weld on the right shows a straight stud, which is also a common application. In all of those cases, you notice that there is a fillet at the base of the stud where the weld has formed between the stud and the plate. Now that fillet is the result of the welding process of a drawn arc welding process, and we'll talk more about that in the next few slides. This photo was provided courtesy of Nelson Stud Welding. Stud welding is a process. Essentially, it draws an arc between the two parts, in this case, usually a plate and a stud, and it forms an arc and allows both the surfaces to melt and then pushes the stud into the plate. And essentially, it's a flash welding process. The difference between conventional flash welding, where both components are usually about the same size, in this case, they are not. In this case, the stud is much, much smaller than the plate that is welded to. But essentially, it is a flash welding process. There are 2 types of stud welding. There's a capacitor discharge stud welding and drawn arc stud welding. And let's look at the differences between the two. The capacitor discharge stud welding, as the name implies, uses a capacitor discharge power supply to produce the weld. In this case, the stud is a special design where it has a stud tip which is integral to the material of the stud. So all of this is one piece. During welding, the stud is pushed down against the plate to be welded. In the initial setup, when the part is loaded and the user will apply a certain amount of force to activate the head. In the second step, when the trigger is pulled and the energy is discharged, the energy starts flowing and it flows through the small tip. And the small tip instantaneously practically vaporizes. And as it vaporizes, it forms a arc, and that arc spreads over the entire diameter of the stud. And the arc provides a path for electrical conductivity for the current to go through from one part to the other. Once the tip has vaporized and the arc has formed, the pressure applied by the spring is going to continuously start to push the stud towards the plate. And at some point, they come together and the fused material from both sides kind of coalesces together and forms a weld. That happens in step 3. So the step 1 is initial setup of loading the stud. Step 2 is firing the electrical energy, which vaporizes the stud tip, establishes the arc, and starts moving the stud towards the plate. And in step 3, the process is complete. the stud stops onto the plate, and the molten metal on both sides will fuse and form a bond. In this case, keep in mind that the stud tip is the same as the base material itself. What are the unique aspects of CD stud welding or capacitor discharge stud welding? First of all, the gun is fairly simple because the stud only moves in one direction, as opposed to the drawn arc we'll discuss in the next slide. And the power supply is also fairly simple. Essentially, it's a bank of capacitors which are discharged and makes a weld. The process is very fast because capacitors discharge very quickly, and they're designed to complete the process in under 5 milliseconds. Because the process is so fast, there is very little chance for the environment to react with the molten metal. So that's why you don't need any shielding gases or protective ferrules or anything like that. However, because the process is very fast, it is not able to make welds in studs which are more than 10 millimeters or less than 3/8 of an inch in diameter, because the arc does not have time to establish in that short time before the stud comes down. The great benefit is you can use cap discharge to weld to very thin plates, especially as in home appliances. So a lot of your home appliances are made of sheet metal, and a lot of them have studs welded on the inside, but you don't see any effect of them from the outside because the process is so fast and there is very minimal heat generation during welding. However, cap discharge CD stud welding can be used to weld to larger plates also. So you can weld to larger plates, but the beauty is that you can also weld to very thin plates. Another interesting aspect of cap discharge is that you can make dissimilar metal welds because there is so little time for the metals to melt and mix that you can actually weld dissimilar materials without having the risk of forming a brittle joint, such as you can weld a brass stud to a steel plate, which would not be possible with the drawn arc stud welding. The drawn arc stud welding is a little bit more complicated than the capacitor discharge stud welding. In this case, the stud, as I've shown over here on the left, has a small tip, which they call flux. The flux oftentimes is essentially a small knob of aluminum or steel studs. So in this case, the stud and the flux are of a different material. Again, in step one, you load the stud into the gun, you apply the pressure and activate the energy. When you activate the energy and the power supply starts to flow that energy, at the same time, there is actually a solenoid which actually pulls the stud back a little bit during this process. So instead of directly going down, it is actually pulling the stud back, allowing the arc to form over an entire diameter of the stud. And that's why the drawn arc stud welding can be used for much larger studs, up to 1.25 inches in diameter usually. So as the arc is allowed to expand and the energy is coming down, you will find a thin layer of molten metal on both sides. At the conclusion of the set time, the solenoid is de-energized, and now we are back to the original process where the pressure applied on the spring pushes the stud down and brings the two parts together in step 4, and then the weld metal solidifies and you have a weld. So the difference between the CD process and a drawn arc is that you're actually pulling the stud back a few millimeters during that initial phase and allows the arc to grow over a bigger area, which is not necessary in cap discharge. But for larger studs, you need to do that. You also notice that you're going to more likely to see a flash, molten metal flash coming out on the sides with a drawn arc stud welding because you have melted more material during this melting process. Let's see what are the attributes of drawn arc stud welding. Greater complication. The gun is a bit more complicated because now it has a solenoid which pulls the stud back. The power supply is often an inverter type power supply. Obviously, that increases the price. But you can make bigger welds. That's the main thing. It is a longer process. Instead of in 5 milliseconds, a drawn arc stud welding typically will take somewhere between 500 milliseconds up to a second. So obviously a lot more time to melt, a lot more time to send the energy. Because the arc is exposed to the environment for a greater amount of time, we need to protect the arc from contamination. And one way to do that is using ceramic ferrules. So there's a ferrule which is placed around the stud. So it allows the high pressure of the arc to push the hot gases out. At the same time, it restricts the amount of circulation of the environment gases into the arc. And it also prevents the fused metal from flowing away too far away from the stud. And I'll show you a photograph of that on the next slide. This process is typically used for larger studs, which are not suitable for CD welding. It does produce a lot more heat because instead of in 5 milliseconds, the weld is now going on for 500 milliseconds. Even if it's half a second, it is still a lot more time. And you're generating a lot more heat, and hence this process is not suitable for thin sheets, and you need at least a 1/8 inch thick sheet for weld to be made. And finally, because we are producing a lot of melting on both sides, this process is not very suitable for dissimilar metal welding because the melt on both sides is then going to mix and form a brittle intermetallic, and that's usually not a good idea. So we cannot do dissimilar metal welding in drawn arc stud welding. Here's a photograph on the left of a stud with a ferrule around it. This is a ceramic piece, and you can see small teeth on the lower edges over here. And they allow for the hot gases to escape when the flashing starts, but at the same time limits the amount of space allowable for the molten metal to flow out. So the stud essentially results in a very unique pattern of fillet around the stud, as you can see on the photograph on the right. These photos also provided by Nelson Stud Welding. After the weld, the ferrule is still there, and it's actually tapped by a hammer and broken into pieces. So one on the right I'm showing is after the ferrule has been tapped and destroyed and removed from the weld. Here's a good example of arc welding versus stud welding, which is those are kind of competing processes, let's say. So if you look on the left, you will see that a typical stud welding stud has been welded to the plate with a GMAW or gas metal arc welding process. Here you can see the fillets on all sides, and you can also see the flux, which is aluminum, has melted during the welding process. So the MIG welding process takes a lot more time, a lot more energy, a lot more expertise to make a full weld, and produces a lot more heat into the weld. On the other hand, the drawn arc welding process produces a weld which is complete joint penetration. So the entire interface is welded, which is not true in MIG welding. Over here, the entire interface is welded, and the process is much shorter. You're doing the entire process in less than a second. It is very robust and requires minimal training. So this is one of the many attributes which are good for stud welding, that the time required is very short, it's very robust, and requires minimal training. And importantly, you do not have to drill into the plate to make that weld. There is a process which is intermediate between CD welding and drawn arc stud welding, which is called a short cycle stud welding. So this is kind of like a mix of both. So here we use a CD welder as a power supply, but at the same time, we also draw the stud back. So it's like a combination of both. Now, this is for stud sizes which are somewhere in between the two, and also commonly used for aluminum studs with shielding gas. So it's a little bit unique, but it can be done. But majority of the stud welding is done with either CD welding or drawn arc stud welding. Let's see a comparison of the two in terms of materials, size, and shape. Here I'm showing you a table with different attributes in comparison for CD welding and drawn arc welding. In CD welding, the stud size is usually less than 10 millimeters, 10 millimeters is a maximum, so it's actually much less than that usually. And in drawn arc, the size is usually greater than 1/4 of an inch and up to 1.25 inches in diameter. So much larger studs can be welded with drawn arc stud welding. For base metal thickness in CD welding, you can use anything. You can use thin, you can use thick, either are an option. But in drawn arc stud welding, because the amount of heat generated is so much, you typically want to use that on plates which are at least 1/8 of an inch or thicker for welding. The stud materials also for both are quite common, or both can do carbon steel, stainless steel, and aluminum. However, CD welding can also weld brass. Brass is a material which is a mixture of copper and zinc. And if you allow it to heat up too much, it starts to vaporize the zinc. So one of the benefits of CD welding is the process is so quick that you can actually melt and freeze brass very quickly and form a strong weld. On the other hand, drawn arc stud welding, because it's a slower process and takes more time and it's a lot more heat, and then the cooling is much slower as well, you can actually use it for alloy steels. So you're not worried about very high rapid heating and cooling, which can be detrimental because the alloy steels can sometimes form very brittle phases. So on one hand, CD welding can do brass. On the other hand, drawn arc stud welding can weld alloy steels. Another difference is CD welding can weld dissimilar metals. So you can actually weld brass to steel, which is not possible with drawn arc. On the other hand, shielding gas is not required for CD welding. You don't even need a ferrule. Whereas drawn arc welding, if you don't use a ferrule, then you do have to use some shielding gas. So in short, a very short welding times for CD welding allows the welding of brass, but limits use of alloy steel. So this is the main difference between the two, is the time is very short for CD welding and time and heat is longer for drawn arc welding. And that results in some choices which are going to be different from one to the other. Titanium studs are possible. You can actually make studs of any material you want, which is weldable. So anything you can weld normally, you can make stud welds out of it. It is just that those are not common. So titanium is not common, but you can make titanium studs. But in this case, titanium is very reactive. So you definitely need argon shielding gas for protection. Inspection of the stud welds is also quite easy. For drawn arc stud welding, you can obviously see the fillet all the way around, and that's a very good visual indication for stud welding. However, CD welding does not produce a lot of flash. So CD welding does not produce a lot of flash, and hence the visual inspection is not as easy in that sense. So in that case, you have to do some mechanical testing, such as a bend test or a torque test. One of those two would work. Aluminum welds are unique in the sense that even if you have a flash, sometimes the shielding was not good enough, say, from the shielding gas. So even with the flash, the weld may not be strong. So that's why you also need mechanical testing. But for cold rolled steel and stainless steels, as soon as you see a nice flash all the way around, you are pretty much assured that the welds are good. More information on these issues related to inspection is on this AWS document, C5.493, recommended practices for stud welding. Now let's see the pros and cons. Welding is from one side. That's a huge pro for stud welding, and that is perhaps the main reason why stud welding is used, is that you do not want to drill into plates either for visual appearance or for issues related to, say, corrosion. So in house appliances, you don't want the holes coming out on the other side, which might be visual to the customer. Or for example, in boilers, you don't want to drill a hole because that produces a very heavy chance for corrosion. So stud welds are very common and popular in certain industries. Minimal heat input compared to other welding processes. As we saw a photograph of a cross-section of an arc weld compared to a stud weld, the arc weld would require a lot greater amount of heat and produce a lot of discoloration and distortion, whereas stud weld would be much, much faster in less than a second and produce minimal distortion. Another benefit is that the entire interface is welded. So the weld is actually very, very strong because the entire interface is welded, and technically that would be considered a complete joint penetration weld. Welding times are also very short, so you can make 100 stud welds in no time compared to, say, any other welding process. You can make dissimilar welds. That is possibility with CD welding because the process time is very, very short, and that allows you to do dissimilar metal welds. And also a great importance is minimal training. You can literally train somebody within a few minutes to make a weld and start welding in a production environment. So there are many pros to stud welding. However, there are limitations as well. The limitation is that the diameter is usually less than 1.25 inches. So you're limited in size to for the size of the studs. And also typically it is a flash welding process. So it is going to produce a lot of arcs, sparks, and spatter. Some of that spatter can be contained by the ferrules, but even then you might have some extra spatter, which may or may not be acceptable under all circumstances. So there are some limitations as well. But all in all, a fantastic process, a very unique process, and very high applications in certain specific industries. Well, I want to thank you for your time and patience in listening to this video and watching this video. If you're interested in learning more about welding and joining, please subscribe to this YouTube channel by clicking the subscribe button at the bottom left. I have many videos on specific topics in the playlist on this channel, including resistance welding, laser welding, arc welding, and so on. So please do subscribe, and I hope you find all these videos to be useful, and wishing you the very best in your efforts to learn more about welding. Take care. Thank you.